Good afternoon, class.
Hey, this is just a shout out to Aaron for being good enough to open today's screencast. Today we're continuing along with protection in operating systems. So today we'll look at how an access matrix can be implemented, access control, revocation of rights, and then capability-based systems and language-based protection. Here are the chapter objectives. So remember, an access matrix consists of the rows are protection domains, the columns or the objects within the operating system. So we could potentially have a ginormous number of columns and a potentially a large number of domains as well. This would generally result in a sparse matrix where many of the intersections of rows and columns, the elements of the matrix are empty. So in terms of an implementation, we could use a global table where you see here what is stored are in essence the elements of the matrix indexed by domain object and the right sense set, which is the element data within the access matrix. So then when a process or user or procedure in domain I is attempting to perform operation M on an object, we search for the ordered triple for that domain and that object and check to see if operation M is in the right set. Table can be large, even though that we're compressing in a sense a sparse matrix, this table could still be large. And with respect to this difficulty that occurs to me in a situation such as this, we could use a wildcard domain that would match any domain. But if you have a situation where you want every domain but one to read an object, that wouldn't fit into this general wildcard mechanism. So option 2 here is to associate the column for an object with the column and then eliminate the empty entries so that what is stored with an object is simply the ordered pairs domain and the right set. And as mentioned here, it's possible to add a default set of rights. So if there is no specific entry for a particular domain, then the default access rights come into play. All right, so this first bullet simply summarizes the previous slide where a column of an access matrix is an access control list. The second bullet is setting up the next slide where a row, and remember that corresponds to a domain, corresponds to a capability list, which are best thought of as keys. So these capabilities define what operations a particular domain is allowed to apply to an object. All right, so here's the actual, option 3 is capability list, which for each domain, that's going to be a set of ordered pairs consisting of object and access rights. So, so in this instance, we're collapsing out the empty entries of a row of the access matrix. This is an important point. A domain doesn't have actual access to its capability list, because if it did, it could modify it. So it simply can reference the capability list, and the capability list is actually maintained by the operating system. So the fourth option is lock and key. Um, the way that I view locks are, in a sense, they're meta domains, and we could have a different lock for various sets of access rights that we would want to give to a domain in order to access an object. So that would be one reason for different sets of locks for one object, just to be able to apply different sets of access rights. Another reason for having multiple locks would be if we want to temporarily grant a set of access rights to an object, but later revoke that without revoking similar access rights for other domains. Because it could certainly be the case that a couple different domains access an object through the same lock. So again, you could view these locks as metadomains, and then the keys are rights for one of the actual domains to transfer to one of these metadomains in order to access the object. So this is a mechanism for, if you think about it, for collapsing, the large set of the large potential set of domains on a system into a smaller number of metadomains. All right, so with respect to this comparison, access lists correspond to needs of users. The users we're talking about here are the users that create objects. So at the time an object is created, the user who owns the object gets to assign access rights to each of the domains. Now, given a particular domain, if we want to know what its complete set of access rights is to all the objects in the system, we have to examine each object in the system to check to see if that domain has any rights. That's going to be time consuming. But the question that arises in my mind is, why would we want to construct that set? We don't, do we care if a particular domain has write permission on a particular object before that domain tries to perform a write on that object? Right, so capability lists, if one does want to determine what the capabilities are within a particular domain, well, capability lists make that easy. But then if one wants to remove all write access rights to a particular object, then each domain needs to be examined. Which is why a revocation of capabilities can be inefficient. So a hybrid approach is to use access lists, and then upon first access of an object, create a capability that's attached to the process, effectively caching the entry within the access list. Eventually, the capabilities need to be destroyed. Well, it's easy to do with the process. That can be done when the process terminates. But things could be a little complicated if it was desired to revoke the capability before the process terminated. So Solaris has this notion of role-based access control to implement the principle of least privilege as mentioned here. It's similar to an access matrix. So a role corresponds to a domain, as we've been discussing, and you can see here that the objects are extended. The notion of an object is extended to include system calls and even options within system calls, giving a rather fine reign of control. And there are mechanisms to allow a user to transfer to a different role. In Linux has the SE Linux extension, which is a similar mechanism for creating roles. I'll also mention in passing that Linux has access control lists as a way of implementing access lists. All right, so with respect to revoking access rights, here are the objects, the options. Is an access right uh, revoked immediately, or can it be delayed? Selective versus general refers to, does it affect all domains, or can we specify that that access right only applies to certain domains? Partial versus total, are all the access rights for the object removed, or can we specify that only a subset of all the access rights be removed? And then finally, is this, if we revoke an access right, is it possible for it to be granted back to the domain at some point in time? So with respect to access lists, there's a good set of options here. The only one that's missing is with revoking an access right from an access list. It's immediate. It can't be delayed. So revoking access rights from access lists is simple, because those access rights remain with the object. When capability lists are used, since those capabilities are associated with domains, revoking an access right requires searching through all the domains, unless we take other measures, such as requiring capabilities to be renewed every so often, or keeping pointers from an object to all of its access rights within the domains, or using an indirection mechanism that would allow us to centralize the access rights, or use capabilities through keys, which I suppose is another form of indirection. So Hydra is a capability-based system that provides a basic set of access rights that the system knows about. Users can declare other auxiliary rights and register those. Those rights are interpreted solely by the user's program, but Hydra itself provides a set of libraries upon which to build those rights. This notion of right amplification is domain, similar to domain transfer. Right, and it's also similar to the syscall mechanism. Remember, with a system call, user process can invoke a system call, change the processor state to kernel mode, and then execute under kernel control, because remember the syscalls are kernel functions, can execute defined privileged operations the system implements those or executes those on behalf of the user, right? So that's what rights amplification is about. I'm going to skip CAP. So the goal of language-based protection is to prevent such exploits as we recently saw with Heartbleed, for example. So in Java, as stated here, classes at load time are assigned protection domains, and then as method calls are made, there's a do privileged method that can add, in essence, capabilities on the execution stack for a thread. And this is safe because a thread can't modify its stack in Java, unlike one might be able to do in C, for example, by taking the address of a local variable and then working backwards in the stack. So in this example, this untrusted applet executes a get with no permissions, no socket permissions, executes a get method in URL loader, which has connect permission for this domain and this port. So it operating on behalf of the applet invokes open within a do privilege, so that adds this capability on the stack. The do privileged executes the open method in the networking class. The open checks that the connect permission is there for the address and allows the method to continue executing. Then following that, this untrusted applet, so all this returns, and this capability is removed from the stack, and then the untrusted applet attempts to do an open directly. So that's a direct call to open in the networking class. The open method checks the permission, sees that there is no such permission on the stack, and that causes an exception to be raised. So that finishes chapter 14, and this is the last screencast of the semester. I hope you found these useful.